Alright, so we're back talking about similarity of triangles. And just as a reminder from the last video, there are 3 similarity axioms. Basically, you can think of it like this. If you know the following, if you know that all 3 sides have a correspondence so that they're in proportion with each other, that the ratio between the corresponding sides is the same, that is side, side, side. If the angles are all the same, if you can find a correspondence between the angles, you know the 2 triangles are similar. One's just a zoomed out version of the other. Same with side, side, side. And the other one is side, angle, side. So if you know that 2 pairs of corresponding sides share a common ratio, and you know the angle between those 2 sides, the included angle. So this is your included angle between the 2 sides. If you know that those are congruent in your 2 triangles, then you know that they must be similar. And I got you to look at a few examples in the textbook just to see how that worked. So what we're going to do is we're going to come up with a way of drawing similar triangles. So how to draw similar triangles. Okay, so basically let's start with a triangle, and then we'll talk about how to draw it. Okay, so here is my triangle. All right, so what I'm going to do first is I'm going to pick let's say, what do I want to say? A special side's not good. Let's pick, we can just say a chosen side. So pick, or a side. So pick a side. So let's say we're going to pick, let's label this A, B, C. So what we're going to do is we're going to pick a side. I'm going to pick AB. This is going to be my side. I could pick any of the other ones. Okay, so this is my side. I'll just put a mark there. Okay, so the second thing I'm going to do is I am going to draw a line anywhere on the page. I'll put a little asterisk here because it's not quite, or maybe the asterisk should be by anywhere, because it's not quite anywhere. We'll talk about that in a second. Anywhere on the page that is parallel to the chosen side. Then after that, so actually let's do that first. So I'm going to draw a line. I don't know. How about right? It can be anywhere. Let me do it right here. So we'll say that those guys are parallel. So the next thing I want to say is extending the other 2 line segments if needed. The triangle made by the opposite vertex. Oh, let me write that a little bit better. Opposite vertex. And the intersection with the other line segments is similar to the original triangle. So, in our diagram here that I just drew, well, we have these intersections with our line segments. Let's call them D and E. So here, we kind of have our big triangle, which is a triangle A, B, C. Well, I'm going to show you that that's going to be similar to triangle. Well, rather than A, B, C, the new vertices are going to be E, D, C. So there's a little triangle that I'm going to make in red is similar to the black triangle. So it's just a scaled down version. It kind of looks like that. But we need to be able to show that. So before we show it, I want to talk about all ways you can draw the line segment where D and E are, just so you can see what's happening here. So let's do it again. All right, so we had this was A, B, C. Let me make a copy of this so I can just draw it. That will do. So I can put it in different places. And I'll need one more. So, the first place I can put it was just like in the diagram that I just drew. Here's our parallel lines. There is D and E. And here is our second smaller triangle. So that's when your line segment cuts through your triangle. Well, it doesn't have to cut through. I said it could be anywhere. Well, how about we make it just outside our triangle? So somewhere outside to the left of our triangle. Well, in that case, we're going to have to extend our line segments a little bit. So we'll extend these. So now this is D here, this is E. And the red triangle I'm about to draw, it's the bigger triangle. This guy here, we're going to I'm going to show you that is indeed similar to our original black triangle. And the third place you could draw it is still outside your triangle, but this time not quite to the left of your triangle, but to the right. So what happens here? So let me draw it. It's not bad like that. All right. So again, we're going to extend our line segments. But our vertices kind of flip here, and we have to be careful with that. So I'm going to call this, I don't know, this one will be E, this one will be D. So the line segment that includes A and D, and the line segment that includes B and E are the ones that are that's what we're thinking are the same in all three diagrams. And in this diagram, it's this triangle here that we're going to show to be congruent. So the only place you can't draw that line, so our star means as long as the line isn't through the opposite vertex. So, again, if this was our triangle, and we drew a line right through C here like this, well, there's no way to extend our line segments. It's just kind of a point. So this is no good. So as long as you draw your line anywhere except going through your opposite vertex to the parallel side to the side that you picked. So this is bad. Everything but that is good. You're always going to make a similar triangle. So now, let's go ahead and I'm not going to do a whole two-line proof for all of them. I'll just do a two-line proof for one of them, and you can see how the argument is going to be the same for absolutely all of these guys. And the key to this is we're going to use our parallel postulate, postulate 7, to allow us to translate some angles. Let me do this on a new page. So we had our triangle that looked something along the lines of this guy. So this was A, B, and C. And I'm going to do the one that doesn't look particularly parallel. It's a little bit better. I'm going to do this one. So these lines are parallel. And I'm going to extend these here. So this is going to be E, and this is going to be D. So now my thought process is as follows. Well, I know nothing about the length of line segments CD and CE, especially in proportion to CB and AC. I know nothing. I just drew my line somewhere, so there's no kind of information there. But I do have lots of angle information, and that's kind of the key. So I know via the X rule, if you will, we have two vertical angles here. They across an X, so they are congruent. So let me put one marking there for that. So these guys are definitely congruent. But also, we know via the parallel postulate, well, imagine erasing this line in your mind, so forget about the line segment BE. And imagine extending line segment AB and DE, so they're lines, and then you have this line segment AD that is a transversal of that line segment. Well, then, doing that, let me kind of just draw it over here, I guess. So we have kind of this situation going on here. So we know that this angle here and this angle here, by our parallel postulate and the angle rule, you can imagine the angle rule is telling us, all right, so here's some vertical angles. Or sorry, by the angle rule, I mean the X rule. So by the X rule, here we have a vertical angle. So we know they're congruent. But we know by the parallel postulate, postulate 7, that we can just translate that angle up to an X on a parallel line. So we just did that. So we have that these angles are congruent. In our original diagram, it means that these guys, let me put two markings, means that those guys are congruent. And then do the same argument that I just did, except with line segment BE being the transversal. So now we're thinking of erasing AD and just having BE. Sketch that on your page if you don't see it right away. But using a similar argument, in fact, almost the exact same argument, we can show that these guys are congruent. So, let's do a two-line proof. So, put our results here and our reasons here. Two-line proofs I find are good for algebra or for geometry. For whatever reason, it just seems to be standard to do it for geometry. Let me erase this line. This doesn't look particularly straight. Let me see if I can make it better. Okay. That's okay. All right. So the first one is angle ACB is congruent to angle, what is it? I guess EC, or D, let's keep the correspondence the same, just because. So let me erase that. So it's angle DCE. And why is that? That is because these angles are vertical, so vertical angles. So that's why I know that they're congruent. And the second angles that are congruent are angle ABC and angle CDE. So that's the ones with the triple markings. And we know that via the parallel postulate. And I guess you're using vertical angles there as well, but I think just saying the parallel postulate is enough, or P7 if you like. And the third one, for the same reason, angle A, hold on, I need A as the angle here, so let's erase that. Angle CAB is congruent to angle EDF, and that's also via the parallel postulate. So I found two triangles where there is a correspondence of congruent angles, so I must guess that these triangles, triangle ABC and triangle, let's get this correspondence right. So A corresponds to D, B corresponds to E, and C corresponds just to C itself. These guys are similar. So not congruent. Triangle DEC is smaller, or at least looks smaller, than triangle ABC. And you could imagine, to be more stark with that, you just move this parallel line closer to C, and you'll get a triangle that's much smaller. Or if you want to make it larger, move it farther away. But the same argument will hold. And so this is via the angle, angle, angle postulate. The book just calls it angle, angle, but I'll call it angle, angle, angle. So I'll put those green brackets just to say the book doesn't include that last one. And let me tell you how I know that. That is via 1, that's our first pair of angles, 2 is our second pair, and 3 is our third pair. So we get that those triangles are similar. And I'll just make a quick note that the argument is similar. For the other two drawings. And you're always going to use angle, angle, angle. Awesome. So let's look at an example of how to use this to measure things. This is a nice applicable result. You could even do this kind of thing with kids if you like, which is really, really cool. So imagine the following. Imagine you want to measure a height of a building. So let's say measuring heights using similar triangles. And heights are just kind of, what do I want to say, arbitrary here. Really, you can use this idea for any distance. Which is cool. But let's do, what do I want to say? Let's do an example. So imagine we have this building. Here's our building. I don't know what it is. Some building. And we don't know the height of it. We want to measure the height. Now, what you could do is you could go up to the top and drop a measuring tape or some sort of device down, but that would be very hard to do. But if we can use the idea of similar triangles to help us, then this will be a lot easier. And the key is as follows, is that the building casts a shadow. So up here is our nice sun. Let me draw a sun. And the building casts a shadow. So let's say it goes to there. We can more easily measure the distance from the base of our building here to the tip of its shadow. That's not a problem. So that is in fact something you can do. You know, one of those wheels that you push along that clicks every meter. You could use something like that and keep track of the clicks. That's a problem that's quite easily solved. I don't even know what those things are called, but they look like this, and there's like a stick and then a wheel, and you push it along and it clicks. You see a lot of sports people use it, but hopefully you know what I'm talking about. Okay, anyway, so we measure the shadow and we get some measurement. Let's say that the measurement in fact is 20 meters. Okay, awesome. So how do we measure the height of the building? Well, with the idea of similar triangles, what we could do is we could take something we know the height of, something nice and small, like, I don't know, a meter stick. So let's take a meter stick and let's put it so that its shadow lines up with the tip of the shadow of the building. So here is our meter stick, and its shadow lines up with the let me use a different color for this actually, so it doesn't look as hard to see. I'll use red. So there's our meter stick, 1 meter, and we can measure the length of its shadow there. Let's just use some easy numbers just to say what it is, but let's say that that shadow, if you like, was 40 centimeters. Okay. And the key to this is as follows. Well, we know the following things. We know, well, the sun's going to create the same shadow angle of anything. So those angles are the same. And the other angle we know that's the same, of course, well, each of these objects, the building and the meter stick, are vertical. The ground is, of course, horizontal. So we know these angles, in fact, are 90-degree angles. That's not super important to us, but we know that they're the same. We know they're congruent. And the last thing that we know, well, if we know two angles of the triangle are the same, because it has to add up to 180 degrees, or you could look at it as, hey, look, these shadows and sun rays are kind of the same line, so obviously this angle here is the same in both triangles as well. So using that kind of same result that we just talked about, you picking a point in your big triangle and drawing a parallel line. Here's our parallel lines. There they are there. So we know those triangles are similar. So by angle, 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 these triangles are similar. Now that we know they're similar, we get all that information about similar triangles. We know the angles are congruent, but we knew that. But we know the sides have the same ratio. That's the key. So let's look at the vertical sides. No, sorry, the horizontal sides, because we know those measurements. So let's do big over small. No, yeah, let's do big over small. So the horizontal length in the big triangle is 20 meters. The horizontal length in the small triangle is 40 centimeters, or 0.4 meters. So let's simplify this just to make our life a little bit easier. I'm going to multiply both sides by 10 just to get rid of that decimal, and then simplify. Lots of different ways of doing it. So this is the same as 200 over 4, which is, of course, 50 meters. So, or sorry, not 50 meters. The units cancel, just 50. So we know the common ratio is indeed 50. So this is great. So what does this mean? So let's call this, I guess, vertical height. Let's call it B, where B is the height of the building. We know the ratio between that and the horizontal side now. It's 50. So let's do vertical side, not horizontal side, vertical side of the small triangle. So the vertical. Well, again, let's do big over small. The fact that we picked putting the big triangle on top, we have to be consistent with that. So the big triangle must go on top. So we called that the height of the building B. The small triangle had a height of 1 meter, and that equals 50. Well, that's easy to solve. B over 1 is the same as B. So B is 50, and the height of the building is 50 meters. So that's a cool example for how to use similar triangles. I do want to point out a couple of examples to look at, or maybe just one example to look at in the book. Maybe I'll just write it. I'll scroll and then write it. So look at example on page 747 for measuring distances over water. So you'll see another example of how to use similar triangles to help you with that